Selamat pagi, kita tunggu kehadirannya Prof. Norita ya.
Assalamualaikum warahmatullahi wabarakatuh. Good morning.
Waalaikumsalam warahmatullahi wabarakatuh, Prof. More than 100 participants, Prof.
Yes.
Yeah, more than 100 participants.
Okay, good. We have around 133 already on.
Yeah,
Yes.
yeah.
What is the total number of students?
The total in electronics subject about 200.
Oh, okay.
Okay.
Good. Well, that's a large number. Very good.
Number identity number maybe. The session will be held with Mr. Nur Aziz Salim, Prof.
Okay.
Yeah.
Noted.
Okay.
Thank you.
Bisa dimulai sekarang, Pak An? Atau
Kelihatannya Prof. Norita masih prepare.
oh, siap, Pak.
No.
Ibu,
I am okay if you want to start.
Oh, oke. Baik, saya buka sebentar. Terima kasih. Ya, terima kasih Prof. Norita dan peserta kuliah elektronika hari ini. Kita berjumpa dengan Prof. Norita dari UITM. Semoga bisa memberikan wawasan tentang elektronik, juga bisa belajar tentang bahasa Inggris, termasuk di dalamnya adalah istilah-istilah yang ada di elektronika dengan bahasa Inggris. Begitu, visiting lecturer program ini diadakan 3 kali, tanggal 2, 9, dan 16 ya Prof ya. Jamnya sama.
Yes.
Ya, insya Allah. Nanti saya bersama Pak Aziz nanti mungkin saling backup. Mungkin pagi dipegang Pak Aziz, nanti sekitar jam 10 ke atas saya pegang. Begitu, sehingga saya serahkan ke Pak Aziz. Monggo Pak Aziz.
Oke, terima kasih, Pak An. Thank you, Prof. Norita, for presence in the electronic lecture. We can start now, maybe, Prof. Norita. For student, please listen and pay attention. Explanation Prof. Norita about material electronic.
Okay. I can begin?
Yes, Prof. Norita.
Okay, thank you. Bismillahirrahmanirrahim. Once again, Assalamualaikum warahmatullahi. Sorry, my voice is banyak makan kuih raya. You know, I got sore throat. But we are online. I think not to worry. It's not COVID. Don't worry. It's not COVID. Because the weather is very hippie and eat everywhere and enjoy the food and the cold drinks. This is what I got. But I'm recovering, okay? Don't worry. Okay, Bismillahirrahmanirrahim again. I am honored to be able to be part of this visiting program, okay? So we are going to look at operational amplifier for today. And we hope that, I do hope that anything that you are unclear or you want to know more, you can always ask at the chat box, or you can always ask me when we provide the Q&A session, or we can always you can always email me. Okay, later on maybe. If you have any further query, maybe during your project, when you are doing your project later on. Okay, allow me to share my slides now. 1 minute. Yeah. Okay. Sharing. Can you see my slide or no? Students?
Not yet, Prof. Norita.
Not yet, huh? Okay.
Yeah.
1 minute. What happened? Share screen. Wait, okay, I think it's here. Okay, now.
Okay, Prof.
Okay, good. Thank you. Alhamdulillah. Okay, so the first of our session today, we will see what is operational amplifier is all about. Okay, as we know, operational amplifier, the short term for operational amplifier, I think everyone knows now, is op-amp. Okay, so when we say 741, everybody knows it's op-amp. It's operational amplifier. It's one of type of electronics amplifier that we normally use to amplify signals, to process signals, and mostly in many electronics applications. Yeah, so we will see today what is the basic of amps, the shall I say the criteria or the criteria of an op-amp, okay, and what can it be used for in various application of electronics and also digital. Okay, this is actually the basic design and function of op-amp. So where this is actually what is being designed and being embedded in the IC, in the integrated circuit. Yeah. The extreme left, yeah, this one, that is actually the op-amp circuitry, which comprise of the basic design and function of an op-amp, where it includes, everybody knows that we use op-amp, be it or not, is actually to amplify something, which means we want to increase the gain at the output stage. Yeah. So this is the symbol of the op-amp. Okay. Op-amp normally is actually like a triangle there, and it has two inputs, which is inverting. The positive is non-inverting, and the negative inputs, we call it as the inverting inputs. And this is the, I'm sorry, this is pin-out diagram, yeah, of a typical op-amp. So again, I just mentioned this to you. We're going to see what is op-amp is all about, yeah. And maybe I'll share later the history of op-amp. Maybe if not today, maybe our next week class when we recap, okay, and the different configuration of op-amp and their application. So practical application of op-amp are as such, yeah. Of course, for signal amplification, we will see how are we going to be able to amplify signals in various applications. For filters, and we will see this next week. High pass filter, band pass filter, low pass filter, etc. For comparators and also as a switch and mathematical operations, which we are going to see today. Okay, how op-amp can actually be used, and we can perform various mathematical operations using op-amp. So when we say mathematical operations, what are the four basic things of mathematical operations? Everybody knows: adding, okay, as an adder, as a subtractor, integral, and also differentiation. Okay, four things. That is the basic maths operation, mathematical operations in our daily life. So how can op-amp actually be used as mathematical operation? Okay, This one is actually inverting and non-inverting op-amp. Okay, so the left-hand side is the circuit diagram and function of an inverting amplifier using an op-amp. Okay, where when we say inverting amplifier, meaning the input is actually fed into the negative terminal, and when we say it is non-inverting amplifier circuit, meaning the inputs are fed into the positive terminal. Okay, so these are the mathematical operations that we are going to see today. We will see how it's going to be as an adder and subtractor. You don't have to worry about the slides because I'm going to pass the slides to your professor after this. So you will be able to have it after our session today. Yeah? Not to worry. I'll pass the whole slide to you. So just stay with me and maybe you can jot your own notes, but you don't have to worry about capturing images or whatever because you're going to have the slides later on, okay? So as an add and subtractor circuit, okay, how it can actually differentiate and also instrumentation amplifier. Okay, we're going to see that later. And integrators and differentiation. Okay, so what we're going to look today is the ideal characteristic of an op-amp. Now, when we say ideal characteristic or properties, meaning something that is theoretical, however, in practical, there are some values to it. Yeah, we want ideally, practically, okay, it is a bit different from the ideal one. So, as an op-amp circuit, we are going to actually look first, what is the ideal properties of an op-amp as a comparator? And we're going to see the effects of negative feedback, okay, related to the gain based on the op-amp. How does a circuit diagram that actually represent inverting and non-inverting? And what does visual earth approximation, okay, means? Okay, normally when we analyze op-amp, there is one term that we always use when we compute or when we calculate, okay, in our design. That is known as visual earth, which means we assume that one of the inputs are grounded so that we can use some assumption for us to compute the gain for the inverting amplifiers. Okay. So what is an op-amp? It is something, when we say low cost, it's not cheap, something affordable. Okay, affordable. The demand is there. It is being utilized in most of electronics applications. Okay, and the wonders that op-amp can do is actually it can amplify signals, okay, to an external power supply. Okay, and it can also be used to perform operations on signals. Okay, this is actually the circuit symbol and pin identification of an op-amp. Okay, and it is fixed. This is what we call pin diagram. Okay, we call this as pin diagram. You don't have to actually hafal, ya, tak perlu hafal. You don't have to hafal, but it's good if you are familiar, because normally when we design or when you go to your lab, you will be given that, or you can Google actually what is the pin identification. Okay, but once we always use it, we don't have problem in memorizing which pins is what actually. Okay, so pin number 1 is actually 1 and 5 is actually offset now, which means we are not going to use it. The second one is inverting input, if we want to use it for as inverting amplifier. The third one is the non-inverting. 6 is always the output. Positive 7 is plus VCC. 4 is for minus VEE. Okay. Okay, and that's what is the pin configuration of our op-amp. And normally 8, we don't connect it. Okay, so this is how it looks like in PCB form and in pin diagram form. Yeah. Okay, normally this is what we connect it in our lab. So symbols for ideal and real op-amp. Okay, for ideal op-amp is this one. Okay, we have inverting inputs and non-inverting input when we have the output. Okay, and there are many numbers for our op-amp, but the most famous one is 741. Okay, and this the one that I have shared with you earlier is also representing the 741. Yeah, this one. But we have another two. So the numbers are different, differ. It depends on which company produce it, manufactured by which company. Yeah. So terminals on an op-amp, we have inverting and non-inverting, and we have inverting is a negative, okay, and the positive is non-inverting, and we have the positive and the negative supply and the output terminal. So in some application, the change in output voltage from the potential divider may be small. Okay, so that is where we actually bring in op-amps, okay, as one of the tool, as one of the purpose to amplify the signal. Okay, so this is actually the 741. It was introduced in 1968, and after that it is so popular until today. Okay, 1960, and you people were not born yet. Okay, op-amp is already out. Yeah. This is the larger version of what is actually the schematic diagram of an op-amp. Again, you don't have to memorize this, but it's good to know that you know what is actually inside the op-amp. It comprises of a transistor, several transistors, capacitor, resistor to make that 741 op-amp. Okay, it's a combination of that is being designed on how it can actually produce the gain or the signal amplification. Normally, when we use op-amp, we are only interested which is the input voltage, the inverting input, which is the non-inverting input, and where are the outputs. But what are the circuits inside the 741 that actually functions and produces the output? Okay, these are the circuits that comprise of several transistors, combination of NPN, NP, NP transistors, and also capacitors and resistors. Sorry, don't worry, I'm not in pain, but I will just cough. Okay, it is actually a device that has all the properties for amplification purpose. Okay, in that IC, it's about 20 transistors. Sorry, we have actually 20 transistors altogether, with resistors and capacitor all formed on a small slice of silicon. Here, everything embedded, manufactured as 8-pin IC. Okay. Okay. So after this, since we already know what is inside the op-amp, what comprise of an op-amp, the circuits and the components in an op-amp. And now after this, we can start using the symbol of an op-amp. Okay. Okay. Op-amp, as I have mentioned earlier, it has two inputs, inverting and non-inverting input, and it has one output. So the inverting input is the one with the negative sign, and the non-inverting input is the one with the positive sign. Okay, so ideally, okay, op-amp requires power to work, which means it needs to be connected to a power supply. Okay, so op-amp have the following 5 key terminals here. Okay, the positive terminal is called the non-inverting input, V positive. The negative, which is Vn. Okay, the output terminal, okay, will be the results of the V positive minus V negative multiplied by A. A is actually the gain. Okay. Sorry. Positive and negative power supplies. Okay, the plus VCC and the minus VCC for it to function. So this is the schematic diagram of our op-amp. Okay, ideally, okay, for characteristic of op-amp, it has infinite voltage gain. So when we say infinite, okay, the truth or practically it is something like 200K, meaning the difference between the positive and negative terminal, the highest it can go to be amplified is around 200,000. Infinite input impedance, meaning there's no current flow into the inputs because the impedance is very high, isn't it? So, in truth, when we say infinite input impedance, it's around 10 to the power 12 ohm, which is very high, of course. And the output impedance is 0 because it allows whatever to be amplified to be sent to the output. So, actually, practically, usually, it's around 5 to 25 milliampere. That is where we say 0 output impedance. And infinite bandwidth, meaning it amplifies and it doesn't have the low and the high. However, it has the range actually. Okay, it has the range, and we will see what is slew rate is all about after this. Okay, this is the 5 characteristics of an ideal op-amp. Sorry. Okay. Infinite input impedance, infinite open loop voltage gain, 0 output impedance, infinite bandwidth, and infinite slew rate. That is the ideal properties. Okay, so when we translate the ideal properties into a diagram, this is what we got. Because the input is equal to infinite ohm, okay, the voltage across Ri is 0. No voltage drop because it's very high. Okay. And when we say it's R out is 0, everything being amplified will be sent to the output. Okay. So here, and this is for the output, for the voltage gain, because we assume all R out is 0. Recall that Z output impedance is 0 output impedance. Okay. Okay. However, in reality, this is the value. There are some input impedance, which is between 10 to the power of 6 and 10 to the power of 12 ohm. Okay, the open loop gain is not infinite, but around 10 to the power of 5. The Z out is not 0, but around 100 ohms. Okay, bandwidth is not unlimited, and there's an effect of slew rate, which is not infinite, around 10 to the power of 4 for every microsecond. So here we actually summarize, okay, what is the ideal value and what is the typical properties of an op-amp parameter. 1 minute, yeah. I just need some water. Sorry. Okay, so we can see here, sorry. We can see here our op-amp parameters. Okay, this is the ideal value, and this is the typical ranges. And this is also the open circuit output voltage for the voltage range and the output voltage. Okay. Okay. Almost ideal op-amp is similar to what I have mentioned to you earlier. Okay. Okay, we will see the first one, which is the comparator circuit. Okay, comparator circuit is actually which is actually to compare two the signals between the inverting and the non-inverting input. Yeah, maybe one of them will be the reference voltage and the other one will be the V-in. Okay, so what's the function of comparator? From the word compare, okay, it is actually to actually determine which signal is higher than the other. It is not using any of the feedback effect. Okay, it doesn't have any gain, nothing to do with gain yet, and saturation output is most positive or most negative value. Okay, that is comparator. This is one example of comparator. Okay, we can look at that. The inverting input, which is negative, and the non-inverting input terminals have rotated here in the schematic, which is fine. Okay, it's okay to do that. Okay, so this is example of voltage comparator. Okay. So when Vs is equal to 0 volt, V out will be 0. When Vs is smaller than 0, okay, which means negative, V out will be positive. And when Vx is larger than 0, V out will be V negative because of this effect. Okay. Okay, this is another one when we use it as a closed loop gain. Okay. So here, for an ideal op-amp, okay, the input impedance we always not assume it is infinite, and the output impedance is 0. So the output voltage will ideally never reach V positive or V negative. Yeah. So that is why the op-amp outputs a voltage V out such that V1 is equal to V2, and this is where we assume that it is virtual ground when it comes to calculation. Okay, and from here, when it is virtual ground, we simplify it to become like this. Okay, so from this circuit, that's how we got, okay, voltage gain A is equal to negative RF divided by R1. Why it is negative? Not to show that the value is less, but because we input the signal at the inverting input, which is the negative here. Okay, that is what we have this to tell that we the inputs are actually fed into the inverting terminal. Okay, so this circuit is known as the inverting terminal. Okay. Okay, so for this one, when it comes to voltage gain, current gain, and trans resistance gain, and also the transconductor gain, okay, the equation is as such. For voltage gain, okay, is V out over Vs. The source for the current gain is I out over Is. And for the trans resistance is V out over I. And transconductance is the opposite of resistor, which is I out over Vs, which is here. Yeah. Good. So we have seen comparator. We have seen negative inverting inputs. So the third one, we are going to look at closed loop gain with real op-amp. How does it look like? Okay, so here we have Is is If plus I1. You have here. And we have I is equal to If or minus I1 is equal to I2 because of the virtual ground. Okay, and we take the V difference, which is V2 minus V1, and you substitute it. Okay, V2 is IR, and from there we will get V out over Vs, okay, which is the gain as this one, R1 over R1 plus RF. Okay, so this is actually for the inverting, for the non-inverting input. Yeah. So the summary for what we have done, the output of an ideal op-amp is a voltage from a dependent voltage source that attempts to force the voltage at the inverting terminal to equal the voltage at the non-inverting terminal. So ideally, when we say ideal op-amp is when we assume input impedance is infinite and output impedance is 0. Okay. And operation of an op-amp was used in the analysis of comparator and inverting amplifier. Okay, so we are looking at inverting, comparator, and this is inverting, and this is inverting as well. Okay, I will stop here. If there's any questions on your part, please ask. Yeah, Giant Drum. Yes, please. You can unmute and ask.
Good morning, Prof. Norita. My name is Gide, and my major is electrical engineering student. I have a question about OPM. Is there any chance noise generated from the input signal we have and the output is mixed with another unwanted signal? And if so, can we minimize the unwanted signal from the input signal given from us? Thanks.
Okay. Okay, when we talk about unwanted signal, the first thing that we need to do is we need to filter it. So in that case, we will use OPM as filter first. Only then when it is clear, then you will feed it for inverting or non-inverting purpose and you will get the gain. Okay? Are you doing a project and you face the problem?
Project about OPM, not yet, Prof.
Interesting questions. Does that help? Does the answer help you? We need to do the filter.
Yes.
We will see our filtering effect next week. Yeah.
Okay. Thank you, Prof.
Yeah. Thank you. Anything else? From anyone, from any other students? We have 136 online. Okay, if there's no questions yet, next week, when we start our session, we will begin with pop quiz, yeah? Okay, which will be based on this week topic. Okay, don't worry, the pop quiz is just to test whether, to test us, to test ourselves, whether we understand what is the things that we should understand. Okay, so it's better for us to know now we have understand correctly or vice versa. That's the purpose of the pop quiz, because the questions is going to be the most of the questions will be the basic things that you should know when it comes to OPM. Okay, so when we understand the basic, the fundamental concept, then you can explore. Because once our basic understanding is not strong or sufficient, it's quite challenging for us to actually go and explore further, you know, especially when you go to your next level to design circuit, to start, you know, combining and design some projects. That's where we need to actually understand the fundamental and the basic concepts. That's why in any subject, I always tell my students, and for you also, we need to ensure that we understand the basic. Because once our basic is clear and we understand it correctly, that's fine. We may make mistakes when we design, but because of the fundamental and the basic that we really understand, we will be able to correct it. Okay? And the same thing when it goes to your, not to mention in your exam, in your questions, things like that. The basic that we need to actually understand. Bukan hafal tau, faham. Faham, why as such? Why as such? That's why we need to always ask ourselves, why? We need to always ask. If we don't understand, start asking. Read, ask, okay? Now we have many sources, okay? We can read, we can ask your friends, ask me, ask your lecturer if we don't understand, or we can read. Don't wait till the very last minute, okay, for you to absorb everything. It's good to understand and actually grasp at the concept and the basic fundamental knowledge of all your topics as every time when you finish your class. Okay. So again, I think all of you have seen this many times earlier in my slides, but I always put it many times because in my opinion, we as human, when we see it many times, inshallah, we can actually record and we can actually absorb. Oh, this is already seen earlier. Okay, why I put it many times? Because I want you to know that in OPAM, the most important thing that we need to know is actually the effect or the function of these two inputs, which is the inverting input from the negative and the non-inverting input from the positive. And it has one output. And all OPAM, it requires power supply to function. Okay. Okay. And how do we compute the voltage gain of an OPAM? Is the difference between the inverting and the non-inverting inputs, and we multiply by the open loop gain of that OPAM. Okay, and we get what is V out. Okay. So the internal OPAM formula is V out is gain times by V positive minus V negative. If the non-inverting is higher than the negative, the output goes positive. That's logic, right? And if the inverting input is higher than V positive, of course, the output goes negative. When we say goes positive or goes negative, it doesn't mean that the value is low. What positive and negative means here is it is actually in phase or out of phase as the input signal. Okay, so with infinite gain, okay, with infinite gain in negative feedback, it looks something like this. Okay, even with load. Okay, and this actually positive feedback methodology, which is normally we will not use it. So the golden rules or the rule of thumb of an OPAM, the inputs to the OPAM draw or source no current, okay, true whether negative feedback or not. The OPAM output will do whatever it can within its limitation to make the voltage difference between the two inputs zero. Okay. Okay. So now we'll go to the inverting amplifier example. And we have seen this earlier, the formula negative R2. Sometimes R2 is called as R feedback. Okay, R2 over R1. Okay. Here it is called RF over R feedback resistor. Okay, so the gain is V out over V in, which is feedback resistor divided by R. Why is negative here again? Because the input source is fed into the inverting terminal. Well, now we are going to see non-inverting. Okay. Now, when we see non-inverting, the resistor is still there, except the input resistor is connected to ground, and the input source is fed into the positive terminal. Okay. So here we know that R1 is V in over R1 to left into ground. Yeah. So what we will determine the voltage gain will be V out over V in. Okay, this is the computation. After we factorize V in here, we will get is as 1 plus R2 over R1. And it is positive because the input source is fed into the non-inverting terminal. Okay, so this is the equation for non-inverting amplifier. Okay, this is one example here. Okay. Okay. So from the non-inverting amplifier, we proceed to the first one of mathematical operation, which is as summing amplifier. So when we say summing amplifier, meaning it is doing some addition there. Addition, okay? It's doing some addition there. Sorry. Okay. So we know that if it is 1 only, it will be RF over R1. So when we have another one, it will be minus RF V1 over R1, V2 over R2, and so on and so forth. So this is actually one of the circuit that when you go for your digital system, you will see how amplifier, op-amp is used as a digital to analog converter. Okay. Okay, it is used as a digital to analog converter. Here. Okay. So if you have 3, it will be something like this. Okay, you remove RF over, not to say remove, you factorize RF over R1, RF over R1, RF over R2, RF over R3, and let's say R1, R2, R3 is the same value. So you will have V out is actually the sum. Okay, the sum of all the the input voltages. So this is bad for you. Okay. Okay, that is as summing amplifier. Okay, I'll stop to summing amplifier. Any question? Okay, summing or non-inverting? Any question on your part? So far, so good. Okay, good. Okay, I'll proceed. So remember, we have looked into comparator. We have looked into inverting, non-inverting, and summing amplifier. Okay. So we will proceed with differencing. Differencing meaning something to do with subtraction. Okay. So when we know that if we have the 2 voltage, okay, the 2 voltages at the positive and the negative terminal, okay, the output will be the difference of the 2 terminals. Okay. So as a differencing amplifier, the non-inverting terminal, which is the positive, okay, the connection is as such so that at R2, okay, we want to know what is the voltage drop at R2. We will use the voltage divider rule, which is R2 over R1 plus R2 times by V positive. And we got what is R2. Okay, so once we know what is R2, sorry, we can compute what is V out. So V out will be V positive 1 plus R2 over R1, okay? And then times by R2 over R1 plus R2, which is the voltage divider, minus by the the inverting terminal, R2 over R1. And that's how it computes the V out, which is R2 over R1, V positive minus the difference between the positive and the negative inputs. Okay, the non-inverting and the inverting inputs. This is actually some simplification being done. You will be getting these slides, and you can actually expand this and make sure you get the one in green after that. Okay. If you have any problem, next week you let me know. I will do it for you. But it should not be a problem. This is just some simple mathematics here. So, in conclusion, for difference amplifier, the formula that we are going to use is the one in green. But how the one in green becomes as such is from these 3 steps. That one you need to know. You just need to know that you can understand and you can accept the formula in green. So when you see the formula in green, you know that it is actually giving us the difference, perbezaan antara V positif dengan V negatif di sini. Okay, and multiply by the resistor R2, R feedback over R1. That's why this circuit is known as the differencing amplifier. Okay, differencing amplifier or as a subtractor. Any questions for differencing? Okay, good. Okay, this is another circuit, which is also for differencing circuit. This is one that we can see, which is similar to this. Okay, it's just the way it is being drawn. It pull it here. Okay, which is used to subtract analog signal. Okay, if all the resistors are of the same value, which means R1, R2, R3, R4, let's say everything is 1K, okay, all resistors same value, we will be receiving V out, which is V2 minus V1, since all the resistors are the same value. Okay. Okay. Okay, this is okay. So here, the next one we are going to see the op-amp that amplifies the difference between the two inputs, which is the V positive and V negative between the two input terminals by a gain of A. Okay. Okay. So what happens here is actually we want to understand how does that happen? The amplification happens or takes place. Yeah. So sorry. Okay. So first and foremost, what happened is actually it will have that negative saturation region, yeah, and from minus VCC to plus VCC, this is known as the linear region. Okay, and when it is saturated here, that is known as the positive saturation region. Okay. Okay. This is practical situation or scenario. This is ideal. We say it is saturated and here perfect zero linear, and here again positive saturation. So during the negative saturation region, V out is equal to minus VCC. This is for the ideal. Practically, voltage gain is V positive minus V negative, and it is less than minus VCC. During the linear active region, which is here, okay, V out is voltage gain AV, V positive minus V negative. Okay, practically, yes, voltage gain V of that difference inputs, which is in between minus VCC and plus VCC. It is greater than minus VCC and it is lower than plus VCC. Positive saturation region is when V out is plus VCC. Okay, and this is actually the linear, the ideal one. But practically is when voltage gain V positive minus V negative greater than plus VCC. So these are the three regions where we actually utilize, okay, op-amp to be as that summing amplifier. Okay. Okay. Now we will see what happened when we go to the lab. Okay, and we will start connect our op-amp, feed it with some values, and how will the waveform behave. Okay, if you set up something like this using RF as R2 as 10K, R1 as 1K with plus VCC minus VCC as plus minus 5 volt. Okay, and this is actually inverting input. Why inverting? Because we connect it to the negative terminal. We know that we are going to get something like R2 over R1, which is 10. Okay, 10K divided by 1K, we will get 10. 10 times the value of V in. Okay. So here, the input is the red, the one in red, which is around 200 millivolt. Yeah. So 200 millivolt, we times by 10, we will get something around 2 millivolt. The one in blue. That's how actually the the signal looks like if we visualize it on the oscilloscope. Okay, so you can see here that the output and input signal is inverted or out of phase because this is actually an inverting configuration since the input voltage is fed into the negative terminal. Okay. Okay, this is another one, which is for the non-inverting terminal. Okay, we have seen that the gain for the non-inverting terminal is 1 plus R2 over R1. Okay, so it's going to be something like 11, 1 plus R2, 10, 11 times by V in. Okay, V in is at 200 just now. So we will get around extra 1 from the gate equation, which is in phase. Okay, the input and the output is same, which is in phase. It is not out of phase. This is out of phase. This is out of phase. Okay, this is in phase. Okay, so that's how we actually check for our input. You know, when you do your project and you know what to look for, this is how you troubleshoot from one stage to another. Okay, on how to check whether your op-amp is functioning and how you're going to troubleshoot which part of your circuit is actually not functioning as expected. Okay. Okay. Here what happened for either configuration, if R2 or R1 is so large, okay. Okay, what happened? The amplitude of the input signal is too high. So that's how it becomes saturated, meaning it has actually reached this part, this saturation, the extreme negative and the extreme positive. Okay, that's why you have something like this. It is being clipped. It is not a perfect sine wave. Okay, it's not a sine wave. It is being clipped up there. Okay, so saturation occurs and the clipping the signal into a square wave. So whenever you see this kind of signal, meaning the ratio of your R2 and R1 is too big. So you need to actually look into that so that it is not distorted or it is not clipped. Okay. Okay. Okay, this is another one, which is if you ever need to have a high input impedance, not that you simply increase R2 over R1. However, you need to have something like this. Okay, R4 over R2, R4 over R3. Okay, this is from the equation that you can still use it if you require a very high input impedance and a high gain. Okay. Okay, the next one is op-amp and summing amplifier and summer. Actually, we have actually looked into this earlier, but what we're going to do is to look at the waveform. Okay. Okay. Here, sorry, it's not there. Here, why is it? Okay. From the scope, from what is on the scope actually, if the input signal is 100 millivolt on both inputs, yeah, the output is going to be 2 volt, which is the pink color. Where we have 200 millivolt times by 10, we get the 2 volts, yeah. Okay. And how do we scale our inputs to have more or less weight? Okay. What you need to do is actually, you need to play around with the value of V1, V2, and so on. Okay, and the value of your resistor, so that you can have what like this one, okay, that for the inputs to be like 10 times or 20 times of your input voltage. Okay. This one, I think I will explain to you next week because this is something like digital inputs. Okay, this one I will not explain this week. But I'll go here, op-amp as subtractor or difference, which we have actually looked into because I want to share with you the how it is being visualized, okay, in the scope. We have known that we have actually computed that from here, R3 over R1, okay, times by the difference V2 minus V1. If all resistors are equal, okay, it will give us what is the value. So here, if we have 4 resistors of the same value 1K, and the input voltage is going to be 2.2, okay? Because this is 1 over 2. This is going to be minus V1 plus V2. 1 over 2 times 1 over 2, we will have 1 over 4. V2 over 4, yeah? Everything 1K, yeah? So that's how the waveform will look like. It's going to give a gain of 2.2 times of V out. Okay, this is another example. If you have a supply line of 9 positive and 9 negative, your V positive is 1.4, your V negative is 1.3. What is the output voltage is if the gain is 10 to the power of 5. Okay, so if we deduct this, it's going to be 0.1 times 10 to the power of 5, we'll get 10,000 volts. So your V out will be 9 volts. Is that possible? The answer is not. Why? Because it has actually exceed or equal to the value of your positive supply line. And it will reach the saturation value, which is this situation. Your VCC and plus VCC is 9 in that case, and your V out is also 9. Okay, so that's the answer. It's not possible. The output voltage cannot exceed the power supply voltage. Okay, and the amplifier is said to be saturated. Okay. Example 2. If the positive supply is 6, negative is 6, V positive is this value, and when we deduct, we will get times by 10, you will get minus 200 volt, times by this, you will get minus 6, okay? Again, the amplifier is saturated. V output, the power supply voltage, in this case, the output voltage is negative, okay? But it is again saturated because the maximum it can go is minus 6. Okay, here, this example, okay, V plus minus V negative, we will get 10. V out, you will get 10. Well, this is fine. It will amplify because your plus VCC and minus VCC is plus 15. So it will not reach the saturation level. It is lower than the value of the maximum plus VCC. So your amplifier will not be saturated. So when you do your design, you need to also make sure that your amplifier is not saturated. Okay? Okay, for this one, for the open loop gain of an op-amp is 10 to the power of 5. If the supply is plus minus 9 volt, what is the minimum difference in input voltages that will cause the output to be saturated? So what's the minimum? It should not actually exceed 9, okay? Plus 9 or minus 9. That is the answer. So here, this diagram shows a circuit that incorporates an ideal op-amp. The voltage applied to the inverting and the non-inverting inputs are V1 and V2 respectively. So what happened at the V out when V1 is greater than V2? What happened at the V out when V1 is less than V2? So when V1 greater than V2, V negative, because what? V1 is to the inverting input, yeah? V negative greater than V positive, therefore V out is negative. So V out will be highest negative 9 volt. And vice versa. If V2 greater than V1, okay, it will be positive. That is what will happen. So for the inverting amplifier, okay, what is actually that we ensure that the amplifier is not saturated is V negative approximately V positive. That is why we got this minus RF over RN. And we use the assumption of visual earth. Okay. And for the inverting, we assume that similarly here. Yeah. Minus RF over RIN also. This is same. And for the non-inverting, to ensure that the amplifier, okay, will give a good saturation, will not go into saturation, V out over V in is 1 plus RF over RIN, where how we got the formula from this equation. Okay. I shouldn't be giving you the answer so that you can. Okay, 1 minute. I stop sharing for a while so that you can start computing. I'll give you some example for you to start calculate. One minute. Take out your papers and pens so that you can start doing the one minute, yeah. Okay, so we are going to, we have 1, 2, 3, 4, 5, 6. Six questions for you to try. Okay. Where is it? Okay, I'll start sharing now. Okay, so now I want you to oh, not this one. Not this one. Oh, this one. Okay. I want you to try to do this. Okay, try this one. The circuit shows an inverting amplifier. The input voltage is 0.44 volt. Calculate the output voltage. Okay, you may begin. I'll share with you the solution. Okay, for this one, the solution is okay. All got the answer correct. Ada any of you cannot do it or don't know how to start, or maybe you did not get the answer? Okay, it's very direct. This is inverting inputs. So the voltage gain is RF over R1. Okay, 22 over 10. And times by the input voltage. So that's the voltage gain. Why negative? Because it's inverting. Okay, everybody good?
Yes, Prof.
Very good. Okay, we'll go to the next one, yeah? This one. What is the value? Wait 1 minute. Something is not correct with this. 1 minute, yeah. It doesn't give any. What is the value of V in? No wonder. Okay, now you can do. Okay, I'll give you the answer. Oh, sorry. Okay, that's the answer. So the voltage gain is 5, okay, inverting 5. And with input 0.2, you will get a voltage output amplified at 1 volt. So when RF greater than R in, of course, the gain will increase. And of course, V out will be greater than V in, increasing. Everybody got it right? Class? Okay, let's go to the next one. Wait. Ini lu mau tutup. Okay, this one. Try and do it first, and I will provide you the solution later. Boleh? Okay, we will go to the next one. Oh, wait 1 minute. Muhammad Arfan, you have anything to ask? Arfan. Okay. You try first. Later, I will provide and explain to you the solution. Because most of the question we have actually gone through earlier, just to make sure that you grasp the concept. So first, state the name of this type of amplifier circuit, how you're going to know which amplifier category sorry, or type is from the input signal is fed into which terminal. Okay. And the next one, why the point P is referred to as virtual ground. Virtual earth, virtual ground is the same thing. Why? Why do we assume that in our computation? Okay. And the last one, it wants you to derive how is the voltage gain for this circuit, okay, is R2 over R1. And yeah, negative is to imply the type of the amplifier circuit, which is inverting amplifier, inverting op-amp. Okay, the solution is here. For the first two, for part A. Okay, and for the derivation of the voltage gain, okay, this is the solution. Okay. Boleh kelas? Ada apa-apa soalan? So far kita dah tengok example 6, 7, 8, 9. Kita ada lagi 2. Anything that you are not clear? Or else we will proceed to this one. Example 10. Okay, the answer to example 10. Okay. Any question on example 10? Okay, so one more, example 11. Okay, try example 11. I'll provide for you the solution soon. Okay, class. We have seen, I have shown you several examples and you have tried out yourself. Example 6, 7, 8, 9, 10, and 11. Would you like to actually ask anything? Especially the examples that I want you to do on your own. Even though there are solutions, maybe you would like to know more. Maybe some of you compute some other ways and did not get the same answer. Students, any questions on your part? Yes, Muhammad Iqbal. Sila. Sila Muhammad Iqbal. Unmute and please ask your question. Silakan.
May I ask something? In example 6, 7, 8, the RF over R, the sign is minus. But
Yes.
in example 9, 10, and 11, why is the sign is positive and why it's +1?
Okay. Thank you.
Or it's saturated, or we use 1 plus R over R when it's saturated or not?
Okay. Okay, thank you, Iqbal.
Thank you.
Okay. I will clarify your question. Okay, Iqbal. For example 6, okay, this example, okay, which formula to use that depends on the input voltage is feed into, dimasukkan ataupun disambung kepada which terminal. Okay, if disambungkan kepada inverting terminal, kita akan guna minus RF over R1 ataupun R input. To show the negative is to show yang input dan output adalah tidak sama bentuk. Dia adalah out of phase. So untuk example 6, input voltage ini dimasukkan ke negative terminal. That is why kita guna RF over Rin. Okay. Example 7 juga, kalau kita tengok inputnya masuk ke negative terminal. That is why we use negative RF over Rin. Okay. And here example 8 juga, input ke negative. That is why we use RF over Rin. Example 9 juga, V in ke negative. That's why we use R2 over R1 or RF over Rin. Example 10, V in masuk ke positive. Ni inputnya masuk ke positive. So this is non-inverting. For non-inverting, the voltage gain is 1 plus RF over Rin. That's why we use 1 plus RF over Rin for the voltage gain. And similarly here, the input voltage is here, tapi di sini juga dia ada voltage divider di situ kan. Tapi inputnya masuk ke positive, which is 1 plus RF over Rin. So the first thing, Iqbal and all of you, you have to be clear. Kita nak tahu nak pakai inverting atau non-inverting, kita tengok input voltage masuk ke terminal mana. Negatif atau positif. Kalau negatif terminal, itulah inverting. Kalau inverting, kita akan guna minus RF over R1. Kalau input voltage masuk positif, itu adalah non-inverting. Kalau non-inverting, kita akan guna 1 plus RF over R1. Iqbal, are you clear now?
Oh, so it's depend on the V in.
Yes.
Oh, okay.
Okay.
Thank you.
Okay, good. Okay, yang kedua, you said macam mana kita nak tahu saturation. Okay, bila kita kira V out, asalkan V out sorry, adalah lebih rendah atau kurang, sorry, that's not the right word. Kalau negatif, dia kena lebih tinggi daripada minus VCC. Kalau positif, dia kena lebih rendah daripada plus VCC. Kalau V out adalah dalam duration itu, dia tidak saturated. Okay? Contoh, sini. Sini tak ada kira saturated kan? Sini. Sini, dia tulis plus 9 volt, minus 9 volt. Kita calculate V out 1.2 volt. So fine. Dia rendah daripada plus 9 volt. Okay, di sini V out dia yang pertama 2.5 volt. So okay. Dia rendah daripada 9 volt. Tetapi V out yang kedua adalah 10 volt. 10 volt lebih besar daripada plus 9 volt. So ini dia telah sampai saturation. Dia tidak akan dapat 10 volt. So paling tinggi dia boleh pergi adalah 9 volt. Sebab supply adalah 9 volt. Iqbal, better now? Boleh faham?
Yes. Thank you.
Very good. Very good. So everyone, if you are not clear, sila tanya supaya you boleh faham. So supaya saya harap Iqbal tanya tadi, kawan-kawan yang lain pun yang kurang faham boleh lebih faham sekarang ya. Okey. Dia dekat sini. Yang saturation. Sebab negative supply kita bagi negative 9. Positive supply kita bagi positive 9. Sorry. Minus 9 dengan positive 9. There is no way it can go above positive 9. There is no way that it can go less than negative 9. Because circuit tu kita dah supply minus 9 dengan plus 9. Itulah minima dan maksimanya. Dia tak boleh pergi turun lagi daripada tu. So kita punya voltage gate kena berada antara dua value itu dan tidak boleh lebih daripada value itu. Jika dia lebih daripada value itu, dia akan pergi ke value maksimumnya. Kalau positif, positif 9 volt. Kalau negatif, negatif 9 volt. Walaupun kita kira sebagai 10, 20 volt. It can never reach 20 volt. It will just go to plus 9 volt maximum. Itu yang saya tunjuk di sini. Kalau kita tengok dekat scope, kalau you nampak you punya output voltage begini rupa, dia macam bukan perfect sine wave, bermakna your circuit sedang menghadapi saturation, which means your VR telah exceed value VCC. Itu sebab dia tak dapat perfect, dia clipkan kepada maksimum. That's why here it clips. Okay, so kalau kita tengok dekat scope, inilah rupanya. Kalau kita calculate, itulah rupanya. Okay, I hope better now for everyone. Okay, any more question? Sebab saya rasa untuk minggu ini, insya-Allah sufficient apa yang kita telah share. Ada apa-apa lagi soalan sebelum kita tutup kelas kita untuk minggu ini? Any more questions? So next week, we will begin with pop quiz. Okay, next week. But before we go for next week, for today, apa-apa that you don't understand or you would like to understand more, please do ask. Kita ada masa lagi. Sila. Students, ada ke soalan kat chat box? Nanti saya cek. Saya pun tak cek. Saya stop share sekejap. Chat box. Chat kita clear. Tak ada apa.
Okay, Prof. Norita.
Yes.
Maybe any question, last question from student? No? Okay, Prof. Norita, saya mengucapkan terima kasih untuk sesi hari ini. Nanti pada sesi minggu depan tanggal 9 dan tanggal 16, semoga kita bisa dipertemukan dengan suasana yang sehat semuanya sehingga bisa mengikuti visiting lecturer ini.
InsyaAllah.
Ya, sebagai host, saya minta maaf jika ada kekurangan.
Saya pun minta maaf.
Terima kasih. Alhamdulillahirobbilalamin. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih, Prof. Terima kasih, Mr. Nur Salim, Aziz Salim, dan juga to all my dear students. Yeah, thank you so much for your attention and your dedication to attend this class today. Okay, we will meet again, inshallah, next week. And please do bring in all the questions that you are not sure. Thank you.
Thank you, Prof.
Thank you, Prof.
Yeah, bye.
Okay, thank you, Prof.
Yeah, thank you.
Thank you, bro.